Right, so let's now just dive into the complications. Your text along the way has pointed out some limitations, quid pro quos, problems, and so on with some of these reactions. We won't spend a lot of time talking about those practical details. I'll sort of leave it to you to be aware of them. As they come up in our practice, we will talk about them. But where it gets complicated in planning a synthesis and in solving predict the products questions is when you have benzene rings that already have two things attached. When one thing's attached, it's pretty easy. You just look at the one thing, is it an ortho para director, and you're done, right? If there are two things, there can be some problems. So from the simple benzene starting material, suppose you do a Friedel-Crafts alkylation with the methyl group. Why you wouldn't just buy toluene to begin with, again, I don't know, but we're assuming you're on an abandoned island somewhere and they happen to have a stockroom full of all the chemicals you want except the ones you need. So yeah, you would make the toluene that way. Let's see, then you would put, let's just suppose you put a nitro group on. And that gets you to the ortho, and you know that the methyl group is an ortho and para director based on our discussion. Then it's clear that the products that you should draw for this reaction are the ortho and the para substitution products and not the meta. Now, suppose that you then want to take this on further. You decide to isolate the para isomer and separate it out and take it on further. So we'll just copy that here. And then you want to be set up for your final reaction where, for whatever reason, you decide, you know, what I really want on the benzene ring, what I really can't live without is a bromine atom. I need to do bromination. What do you do here? Well, you need to consider the characteristics of the two groups. We're going to do this with some highlighting. The methyl group is an ortho para director. So the methyl group would prefer substitution at orthocarbons and para. It can't go here. Why can't it go there? Why can't we put the electrophile there? Because you've never seen it before and it doesn't make sense. Well, let's just remember the mechanism of the reaction. If you did substitute at that carbon, what's your problem? Sorry, that sounded kind of aggressive. What's your problem, man? What can't happen? You can't regenerate the arene by removing a proton, right? The only carbons that we can use in electrophilic aromatic substitution reactions are carbons that have hydrogens on them, okay? Carbons that are already attached to something, sometimes that's called the ipso carbon. There's no ipso substitution in electrophilic aromatic substitution because you can't re-aromatize. The nitro occupies the position where the proton would be. So that's why I'm not even going to highlight the para position there because it's already substituted. Now let's look at the characteristics of the nitro group, which you know are meta, it's a meta director. Identify the meta carbons relative to the nitro. There's full agreement actually here as to what happens. The ortho and the ortho para director is in agreement with the meta director, and so it should actually be trivial to put the bromo on the carbon that is ortho to the methyl group and meta to the nitro group. Does that make sense? Pretty easy, okay? That's when groups agree. Of course, you can envision situations in which the groups might be in conflict. So let's suppose you take this methyl or para-nitrotoluene, and for, again, some inexplicable reason, you say, let's actually reduce that to the aniline. And maybe let's do something else to the aniline first, just for fun. Let's go ahead and make the acid chloride. We'll do the amide bond formation with the aniline to turn it into this amide. And then let's suppose after that we want to do the bromination reaction. Now, again, let's look at the characteristics of these two different groups. You have the methyl group, which you know is an ortho and para director. So we'll highlight the carbons that are ortho to the methyl group. Then we have this amide attached to the benzene ring through the nitrogen, and that's on our list of ortho and para directors as well, which means it's going to prefer these two carbons. They're in conflict, right? Two directors in conflict. The principle when you face that situation is the strongest director wins. All right? So we would now need to have a feel for the ranking order that we got earlier, where we find that the resonance donating effect is more powerful than the inductive donating effect. And therefore, we would predict the bromo group to go on the carbon that is ortho to the nitrogen and not on the carbon that's ortho to the methyl group. Right, so that idea is strongest activating group wins. Questions about that? Yeah.
Could you remind me why the amide there is a
Why the amide group is a donating group? Because it's got lone pairs on a heteroatom adjacent to the benzene ring.
So
Those lone pairs can still donate into the ring. Now, the amide group is less of a donating group than the straight up aniline. And the reason for that is the adjacent carbonyl has another place these lone pairs can go. So it's not as donating as this one, but it's still donating. Yeah. Yeah, still that resonance happens. Good, others? Some of you may actually, probably not many of you, but some of you may be wondering why we bothered to make the amide in the first place. Couldn't I have just made the same point by trying to do the reaction with the aniline and putting where the bromine is? Yes, I could have. However, your text points out that the anilines and phenols are so activated that so much more nucleophilic than benzene, that they tend to have problems with the bromination and chlorination halogenation reactions. In fact, what is commonly seen as a sort of, and this is one of these problems that I told you your text would talk about, and we'd maybe deal with it as it comes up. One of the problems that you see with anilines and phenols is if you try to do the Lewis acid catalyzed halogenation, it turns out that because the aniline is so much more nucleophilic than benzene, you actually get over halogenation, which is great if you wanted tribromoaniline. A workaround for that There's a couple of workarounds for that. One of them is, your text points out, you can use the aniline and just straight up bromine, no acid catalyst, and that will give you the desired monohalogenated product, which is fine. The other option is to do what I did, where you take the aniline and you tune down its reactivity by doing nucleophilic acyl substitution with the acid chloride to make the amide. That cools off the aniline as a donating group. It's not quite so donating, still an ortho-para-director, but then you can do the halogenation reaction without worrying about over-halogenation. All right, other questions? Lastly, I think talking about sort of what to do when, you may find yourself in a situation, let's see, how can we deliberately fall into this situation? I'm trying to think about how best to do this. Okay, maybe. Shoot, I'm trying to think off the top of my head. Anyway. So let's suppose you find yourself in a situation like this, and what are you going to do? Let's do aryl nitration. You've got the chloro group, which is deactivating relative to benzene, but which nevertheless is still an ortho-para-director. And you have the ketone, which is deactivating relative to benzene, but is a meta-director. So the ketone prefers this carbon. Sorry, if it's okay, I'm going to switch to just an OH. At this stage, some of you are going to be thinking, how could I have made this to begin with? Don't worry about that. We haven't talked about how to put phenols on benzene rings. We might get there this semester. We probably won't. You're seeing a problem. I can't start with the phenol and put this group on, because how would I have gotten the meta substitution, right? Don't worry about that. Just take this as a starting point. The phenol, the OH, is going to prefer ortho and para carbons. The ketone is going to prefer the metacarbon indicated. How do you know what to do? There's a couple of things going on here. Your text doesn't make this totally clear, though in problems it expects you to come up with this. So I'll just show it to you here. The strongest, you're going to use the principle, the strongest activating group wins. And of course, the ketone is a deactivating group, so that means we're going to follow the regioselective preferences of the phenol. Okay? Now, that's kind of difficult. The place where your text gives you the most explicit example of the strongest activating group wins is, oh, we didn't do that either? Yikes. Oh, is this one, right? Where you have two activating groups and the strongest activating group wins. That's when two activating groups oppose each other. Apparently, you can use that principle as well when an activating group and a deactivating group oppose each other. Okay? I don't, yeah, so when you're in that situation, the strongest activating group wins. Now, of the 3 carbons that we could put the electrophile on, which should we choose? There's, you've got 2 orthocarbons and a paracarbon. It turns out this orthocarbon in between the 2 metagroups is a problem because of sterics. When those 2 groups that are meta to each other are already in place, you don't generally observe a substitution product in between them, mostly because of sterics. So the 2 products that you would expect from here would be the ones where the electrophile, the nitro group, ends up on the orthocarbon relative to the oxygen, and on the paracarbon relative to the oxygen, but not the carbon that's in between the oxygen and the ketone. Right? Okay, so now let's practice and do some retrosynthesis. And this is where you really test how well you can understand some of this stuff, because you got to account for sort of all of the problems. So we'll start easy and we'll get more difficult. Or maybe they're all difficult. All right, so this happens to be 20.61 C in your text. So, and the rules are you've got to start at the very beginning. Your allowed starting materials include benzene, alkyl halides of 5 carbons or less, and then any other reagents that you need. So we start by noting the groups that are on the benzene rings, and we try to get a feel for the orientation, the relationship between those groups in space, and how we might have gotten things on and in what order to get the desired regioisomer as product. So one of the things I note, let's just highlight that aniline. I don't know how to put the nitrogen directly on the benzene ring, but that I know that that probably used to be a nitro group. Okay, that's all right, but I know that when it was a nitro group, it currently is an electron donating group and is an ortho and para director. Prior to that, when it was a nitro group, it's a meta director. Now I'm looking and I want to see, are there any groups that are meta to that aniline? If there were, that would tell me that those groups needed to go on when the aniline was still the nitro. There aren't, they're still ortho and para, so that maybe gives me the idea that the nitrogen was on early. Okay? How about the alkyl group? We'll highlight that. The alkyl group is currently an ortho and para director. I see the nitrogen ortho to it. I see the bromo meta to it. So that's a potential problem, right? That means there's going to be a conflict at some point. If I were to have put the alkyl group on first, that maybe doesn't explain how I got the bromo group there. Finally, looking at the bromo group, it is also an ortho and para director. I see the nitrogen on the ortho carbon. I see this on the meta carbon. So yeah, how to get these two meta to each other is maybe something of a challenge. All right. A couple of, if you've been keeping up with the text, there are some practical issues which are going to influence the best synthesis. And the practical issues are these. I notice I've got the aniline in the product and a bromo, so I know that I'm going to need to beware of over-bromination of anilines. And then the second thing that I want to beware of is something that's mentioned in the section on Friedel-Crafts. Beware of anilines in Friedel-Crafts reactions. And the reason for this is that the Friedel-Crafts reaction depends on the presence of the aluminum catalyst to turn the chloro into a good leaving group. What happens with straight up anilines, not with amides, but with anilines, is that the lone pair on the nitrogen will dump into the empty p orbital in the aluminum, and you'll get this Lewis acid, Lewis base sort of adduct that shuts down the reaction. So, you know, I'm thinking if I was going to do a Friedel-Crafts alkylation, probably I want to do that before the aniline is there. And then it turns out Friedel-Crafts are pretty problematic. The other warning on Friedel-Crafts is beware of Friedel-Crafts on resonance deactivated benzene rings. So you see my problem? I want the alkyl group to be there, but it can't go on when the aniline's already there. I can't also put it on if the nitro's there, because the nitro shuts down the Friedel-Crafts reaction. Those practical concerns tell me I probably want to do the Friedel-Crafts reaction first. All right? So let's just try, this is a different kind of retrosynthesis than what you saw before. We could have used retrosynthetic arrows and thought backwards, but when you do this, you need to try multiple times because you're going to think backwards and then come up with a problem. I'm trying to help you foresee these problems. Let's just start at the beginning and see what problems we encounter. So suppose this is attempt 1. Can't remember whether or not it's going to work, so let's just go for it. Suppose we decide to do the Friedel-Crafts alkylation first. Your text says that this is going to be a problem due to a weird rearrangement which we are ignoring. So we're going to put a big smiley face on that and say, yay, good job, and we're going to move ahead. Okay, so what about that? What am I going to do? What should I do next? Yeah, go ahead.
Could you just get around that by doing acid chloride with an ethyl group and then just removing the oxygen with
So you could get around that rearrangement problem, yes, by doing the acylation and then reduction. Well, let's see if that's necessary. It's not going to be necessary for us because we're pretending like carbocation rearrangement isn't an issue. We'll see whether we can get the regioselectivity right if we do it this way. Okay, what should I do next? I've got my ortho para director in place. Suppose I do the bromination next. Is that a good idea or bad idea? Why is that a bad idea? Because it's going to put the bromo on the ortho and para carbons, and that's not what I want, right? All right, let's try Putting on the nitro group first then. That puts, let's see, I would get this desired ortho product. Remember, the alkyl group is an ortho para director. I assume that I'm going to, this is where I was telling you in a synthesis, if you get both ortho and para isomers, just take the one you want and move forward, assuming you can separate them. Okay. Now what do I want to do? I still can't put the bromo in place because the activating group would, let's see, my preferences are for ortho and para substitution still. The nitrogen is, the nitro group is also going to favor these positions, meta to the nitrogen. So right, I'm going to want to first reduce to the aniline. Okay, and then what? Now let's look at the preferences. I just switched the nitro group from being an meta director, now it's an aniline, it's an ortho para director, versus the alkyl group, which is also an ortho para director. Strongest donating group wins. So then what? So then I can do the bromination reaction. Should I do this? Probably not, because beware of overbromination of anilines. So I could simply leave out the Lewis acid catalyst. And that would give me that desired product. Okay, so that's probably, go ahead.
If you were to overbrominate, would you get the other bromine to overgroup on the other reversal?
Shoot, I don't know. It's a good question. If you overbrominate, could you get it, since you got two different activating groups there, could you, what type of regioisomers would you get? I don't know. Be interesting to go to the lab and try that out. One of the most, other questions? Sorry, yeah.
How do you know when it will overbrominate versus react with the catalyst?
Good question. Overbromination is for the halogenation reaction. Reacting with the catalyst is for Friedel-Crafts. So apparently nitrogen attacking the iron isn't an issue, but nitrogen attacking the aluminum is an issue. You may sort of wonder, why are we getting bogged down in practical issues? You got to understand that the author of your text, Professor Smith, is a synthetic organic chemist. It is her career to like make things in the lab, and you've got to know this stuff to avoid problems. So in some ways, she's training all of you to become synthetic organic chemists someday. And if you want to get in the lab and have some experiences in this way, you should talk to some of my colleagues, Dr. Michaelis, Dr. Castle, Dr. Andrus, Dr. Peterson, Dr. Savage, who are doing a lot of complicated syntheses all the time. And they deal with these practical issues. Some of them you can anticipate ahead of time. Other times you try a reaction you think would work and it doesn't work, and then you got to figure out why. These are some cases where people have tried reactions that they didn't work. They sort of figured out why. They now pass that information on to you so that you can be wiser than they have been. All right. Now, one of the most vexing parts of planning a synthesis, especially in this chapter, is where you plan something you think would work, and then you look it up in the key, and their answer is different. Yeah, go ahead. How am I going to test you on the practical issues? The way these questions tend to be formatted is I give you a starting material, I give you a product, and then I give you 4, 5, 6 alternate pathways, and you choose the one that works. Yeah?
So I know you already described it, but I'm still having trouble understanding like how to know which of the strongest group is going to win. Like, what are we basing that off of again?
The rank order that we talked earlier. Which of the strongest groups is going to win? How do you know that? Empirically, based on observations as to which groups are more activating. The strongest activating group.
Okay.
has its regioselective preferences honored.
Okay.
Yeah.
Kind of following up on that, this might be a dumb question, but one time you said the strongest director wins, and one time you said the strongest activating group wins. Is there any difference between those two?
I think I had the text in front of me and I tried to repeat what the text said. It is true that your question is, I've said before, strongest ortho and para director, strongest activating group. Which is it? We've discussed the issues of reactivity relative to benzene and regioselectivity separately. This rank order is actually in order of reactivity relative to benzene. I don't know that, because you can actually measure that with reaction rate. I don't know that you can measure strength of ortho, para, regioselective preferences. So the strongest activating group wins is probably the right way to think about it. I don't think that distinction actually matters. I don't think it gets you to a point where you'll make the wrong choice, but just trying to be consistent with the text. Yeah, thank you. Yes?
So can Friedel crafts only happen with benzene that is associated with alkyl groups? Or
Can Friedel crafts only happen with benzenes that are substituted already with alkyl groups? No, you just can't have a resonance electron withdrawer on it.
I know it can't happen with halides, right? Like
Thank you for pointing that out. That is an easily misunderstood limitation. The Friedel-Crafts reaction, alkylation, involves basically a carbocation intermediate. So here's an example, where in which the leaving group leaves in sort of SN1 type fashion to give you a carbocationic intermediate, and then the benzene ring attacks. Your text says that as electrophile, you can't use the following, and that's vinyl halides and aryl halides. And the reason for that is because vinyl and aryl cations are too unstable. What your text did not mean to communicate is that you can't use aryl halides as nucleophiles in the Friedel-Crafts reaction. That's totally fine. So if I wanted to do a Friedel-Crafts reaction using the aryl halide, presumably that would work fine. And you're welcome to do that, and I think there are examples in your text where that's done. So don't misinterpret that. They mean by the aryl halides not working in a Friedel-Crafts reaction as electrophiles. Yep, good. Others? Let's talk about alternative methods, because I know one of the things that frustrates you most is that when you've planned out a synthesis, you think it works, the text says something different, and so now you're afraid that your synthesis is wrong. The standard for synthesis questions is your chemistry has to work. Fortunately, in the multiple choice format, you're sort of directed in some ways. You're not going to go off into the wilderness and try to make up new reagents. But in general, if your chemistry works, great, don't worry about it. Now, I realize that that's not helpful because you're students. How do I know if my chemistry is going to work? Let's sort of think of an alternative possibility other than the one that we've talked about. Can you think of another way I could get every group in the right place while dodging some of those issues that we've talked about? Okay, at least one alternative that we mentioned a while ago was, what if we put the 3 carbons on as an acyl group? What would our motivation be for doing that? Let's just see. As I said, part of the motivation for doing this could be to avoid potential carbocation rearrangement, but let's just give it a try and see whether it works. So if we put the acyl group on first, all right. Now what do we want to do? Yeah, maybe now it's a great time to put on the bromine group because we've got a meta director. We used to have, ultimately we know that this needs to be an alkyl group, but in its current form, that's a meta director. Maybe this is a great opportunity to have a conflict-free bromination, and it also allows us to install the bromine at a time where we're not worrying about the potential for over-bromination because we don't have an aniline there. So in some ways, this approach dodges the conflict that we set up in the last step, where the bromo could go in one of two different places, and it also dodges the reason we had to leave out the Lewis acid catalyst. So that could make us feel okay. All right, how about now? What am I going to do? If at that point I want to install the nitro group, I could go ahead and do it because I've got an ortho paradirector in the bromo, and I guess we were using pink for the bromo. The ortho paradirector for the bromo versus a meta director for the ketone, and we've said the strongest activating group wins. Although we know that bromo is slightly deactivating relative to benzene, so maybe that's a bad idea. Maybe it would be better, rather than to set up a conflict, to just, as some of you were saying, let's reduce the ketone to the alkane. I'm choosing one of the two conditions that I said you could use for this. Zinc HCl is the other. Either of those work. That then puts me in this situation where now their preferences should reinforce each other. Ortho, and para. Ortho and para. We know that we're not going to substitute at the one that's in between the two groups that are meta to each other. So now I can do this sort of late stage nitration to put the nitro group on. Of course, there are two possible places it could go. I choose, I assume that I can separate the ortho and the para isomers. And then finally, at this late stage, I do the reduction. Now, my guess is if you look this problem up in your book, this lower method that we have done is probably the one that's in the key. And the reason it's there is because it dodges all of the issues that we talked about. Yeah? I think you lost a carbon. I'm sorry. Sorry, I have teenagers. This is how you respond to people that criticize you, is that you just throw it back in their face. You are correct. Thank you for pointing out that we lost the carbon. And you can feel free to put that in the end of semester evaluations. Dr. Price insults students when his mistakes are pointed out. Okay, so other questions? Yeah.
So just the overbromination, is it only a problem when there's already like substitutions on the benzene ring, or is it always a problem?
I think the problem, overbromination, I think is only a problem with the anilines. I mean, I can look that up, but, okay. The book said overbromination is a problem with anilines and phenols when you have OR, OH, NH2, and so on. Right. So yeah, it's only a problem if you have the this category of groups on the ring. The anilines or the phenols or anisols, not for the amides or the esters, because these are tuned down in reactivity relative to the starting material, or relative to benzene. Okay. Should we do more? No, let's just go. Yeah, let's do more. All right, this is 22.61D. All right. So sometimes when you're doing this, you want to look at the product and try to decide what groups you could have put on directly, such as the chlorine, sort of one and done, versus what groups you might have needed to put on and then do something to. For example, looking at that alkene, I'm going to remind myself that I can't use the vinyl halide in a Friedel-Crafts reaction as the electrophile. So there's no way to put that on directly. And so I want to be thinking, how could I have gotten that there? And so I'm just planning out, maybe this used to be the benzylic bromide, and maybe that used to be the corresponding alkane. That's probably what I'm going to have to do there to get the reaction to work. And that sets me up with a problem, and that is I already have benzylic CHs here. So if I ever were to go, if my plan involves an intermediate, and I'm just sketching this out, if my plan involves an intermediate like that, that's a bad plan, because there's not going to be selectivity for these benzylic hydrogens versus these ones. Okay? Another issue I've got is this meta relationship between the alkyl group and the chloro. All right, so we sort of got our work cut out for us. Probably the idea is that if I'm going to do this to get this alkene here, that's got to be done before these benzylic protons show up. Okay, so let's think of a strategy. If that's true, the other sort of issue is I'm not sure I know whether the alkene is an electron donating group versus a withdrawing group. It's probably not a withdrawing group. It's probably also not strongly activating. You remember, if it were a CH3 or an alkyl group, or I don't know how electron donating it is. If it were an alkyl group, the sp3 carbon of the alkyl group's less electronegative than the sp2 of the ring, and so that's an inductive donor. This is probably less inductive donating, because now it's an sp2 carbon, which should be similarly electronegative to an sp2 carbon. So in addition to trying to figure out when I'm going to do stuff, I'm also not sure how to deal with the regioselective preferences of that group. So probably I'm going to want to get things in place prior to making the alkene. So how could I do that? And one idea is maybe this one down here used to have been the acyl group and lacked benzylic protons entirely, so the radical issue is not going to be a problem. So from that perspective, starting with benzene and just sort of planning things out, And sometimes we'll just call this attempt 1. Along the way, we may have to abandon this attempt if we figure, if it looks like we've got a problem. We'll do the Friedel-Crafts alkylation first. Then let's follow that up with Friedel-Crafts acylation. Why did I do the alkylation first before the acylation? That was deliberate. Go back up to our practical issues. Beware of Friedel-Crafts on resonance deactivated benzenes. Once you put the acyl group on, that's a resonance electron withdrawing group. That makes the subsequent Friedel-Crafts reaction too slow because the resulting benzene ring is not nucleophilic enough. So that's why I sort of made the choice 1, 2, 3 carbons, is that right? Ish, yep. Okay. How about now? What do you think? Probably I want to get the chloro in place because at least at this point there are groups that I know how to think about in terms of their regioselective preferences. The ketone is a clear meta-director and should prefer these carbons. The alkyl group is a known ortho-para-director and should prefer these carbons. Their regioselective preferences reinforce. So the next step is probably a no-brainer. Let's just put the bromine group on there while all of our ducks are in a row. Okay. And so now we've gotten everything in the right place. We just now need everything to take its final form. Remember, I said our strategy for getting the alkene there has to involve radical bromination of the benzylic carbon. I want to avoid having these other benzylic protons there. So my guess is that at this stage, we do the radical bromination first. I need more space. Okay, that's going to install the bromo group. And radical bromination is selective for the more stable radical. Then I could do the elimination reaction, perhaps with tert butoxide. My ketone is still in place, and only at that stage do I reveal the ketone. Again, you could use any of those two sets of conditions for reducing the ketone to the alkane. Oops. And that's my desired product. Okay, so yeah, go ahead.
I was just going to say, I think you accidentally changed it to a bromine when we were initially trying to give it chlorine.
I think you, I'm sorry, I was about to say, I think you accidentally changed it. Sorry. You are absolutely right. Thank you for that. FeCl3 and then chloro. This is why it's good to study in groups, so you can have friends point out the stuff that you forgot that you can't see, because I totally didn't see that. Thank you. All right. So we've gone through this kind of quickly, and you haven't probably had a lot of time to test out all the possible alternatives and to come up with, get yourself into a corner where it's not working and you can't get the groups in the right place. You need to have that experience. You need to approach this from a scientific point of view where you're just going to try and see what happens and learn empirically from your own mistakes, because there's probably not a way I can write out a decision tree for you that's, if you follow it to the letter, you just will never make any mistakes. No, you have to learn by trying these problems and getting in a position where it doesn't work and I get stuck, and then you get help and find a workaround. Okay? So I recommend you do that. I think there are, of the questions on the exam, I think 3 of them are sort of chapter 20 style synthesis questions that you should be prepared for. All right. Good luck. May the force be with you. My office hours are today from right now till noon. And I will see you Friday when we'll move on to the next chapter.